Hello friends, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University. In our past session, we had discussed quotient rule, product rule. We had also discussed about differentiation of exponential and logarithmic functions. And we had also learned how the concept of limits and continuity is required to understand the concept of differentiability. Now, in this session, we are going to extend our discussion of differential calculus to few more advanced concepts, likewise chain rule and many more. Again, I request you that if you had practiced the ample number of numericals problems which are given in your self-learning material, then only you will be able to understand this session in a better manner. So the objectives of today's session are in fact to understand and apply the chain rule and perform the differentiation of the parametric form. Apart from this, how to determine the second order derivatives. So we are also going to understand what second order derivatives are and how to determine them. Let's understand about the concept of the chain rule. The chain rule is applicable to the functions which are composite in nature. We had already discussed about the composite functions when we were discussing about the concepts of the limits and continuity, wherein we discussed that the composite functions are of the type FOG or GOF. And we learned that FOG of x represents f of gx. So if we are having composite functions, then how to perform the differentiation of such composite functions? The solution is nothing but chain rule. What is in fact chain rule? The chain rule says that if say y is function of u and say u is function of x, then derivative of y, that is dy by dx, will be how to perform this dy by dx. The solution says dy by dx is nothing but dy by du into du by dx. The chain is formed by the parameter u. So that's why this is called chain rule. So we learned that composite functions are of the type FOGX, that is f of gx, and the chain rule says that derivative of FOGX is derivative of FOG into derivative of g. So this simply says that ddx of f of gx is equal to derivative of f of gx into derivative of gx, and it simply says that if y is function of u and u is function of x, then dy by dx is dy by du into du by dx. So this is the formular definition, and this chain is established by this parameter u. So that's why dy by dx is dy by du into du by dx. So we can have further more complex chain, say if we are having more composite functions. Likewise, we had discussed f, o, g, o, h of x. Then how to find the derivative of such a function y. Again, the chain rule is a solution, that is if y is function of say u, u is function of say v, and v is say function of x, then dy by dx will be given by the expression dy by du, du by dv, dv by dx. So here the chain is formed by u, here the chain is formed by v. So I hope you understood what the chain rule is all about. The chain rule is about determining the differentiation of the composite functions, wherein one function is the function of other variable. Likewise, we had discussed y is function of u and u is function of x, then dy by dx is dy by du into du by dx. So let's apply the concept to find the derivatives of the following functions. Say over here the first function is y is equal to x square plus 1 whole cube. So y is equal to x square plus 1 whole cube. You can say u is equal to x square plus 1. So you can say y is nothing but u. So in order to determine dy by dx, you are supposed to determine dy by du and then du by dx. So what will be dy by du? Dy by du will be equal to d du of u cube. Applying the power rule, 3 into u to the power 3 minus 1, that is 3u square will be dy by du. Similarly, du by dx will be equal to ddx of x square plus 1. This turns out to be 2x. So du by dx is 2x and dy by du is 3u square. Now applying the chain rule, dy by dx will be equal to dy by du into du by dx. So dy by dx is equal to dy by du into du by dx. What is dy by du? Dy by du is 3u square and du by dx is 2x. So that means what is u in fact? U is x square plus 1. So substituting the value of u, you get the answer 3 into 2 is 6. So 6x into x square plus 1 whole square. So I hope you understood that by applying the chain rule, we solved the first question wherein the given function was y is equal to x square plus 1 whole cube. Now applying the concept to solve the other question wherein y is equal to e to the power x square. Taking u is equal to x square. So let me solve it for you for your better understanding. If we take u is equal to x to the x square, then it will transform to y is equal to, we are given y is equal to e to the power x square. Taking u is equal to x square, you will get y is equal to e to the power u. So du by dx turns out to be 2x and dy by du turns out to be e to the power u. So that means dy by dx is equal to dy by du into du by dx. What is dy by du? Dy by du is e to the power u and du by dx is 2 into x. And what u is? U is x square. So substituting x square in place of u, you get e to the power x square into 2x. So the answer is 2x into e to the power x square. So this is how we apply the chain rule. You can, on the same lines, you can apply the chain rule to solve the problem of y is equal to natural logarithm of 2x square plus e to the power x, wherein you can take 2x square plus e to the power x as u. So taking u is equal to 2x square plus e to the power x, this expression y is equal to natural logarithm of 2x square plus e to the power x resolves to natural logarithm of u, because we are taking u is equal to 2x square plus e to the power x. Now applying the chain rule, we need to calculate dy by du and du by dx. So dy by du, that is y is equal to natural logarithm of u. So dy by du will turn out to be 1 by u, and du by dx will be equal to ddx of 2x square plus e to the power x. So that turns out to be 4x plus e to the power x. So substituting the value dy by du and du by dx in this chain rule expression, you will get the expression 1 by u into 4x plus e to the power x. Substituting the value of u, the value of u is 2x square plus e to the power x. You will get the final solution as 4x plus e to the power x upon 2x square plus e to the power x. On the same lines, we can solve the expression y is equal to x plus natural logarithm of x whole square. So taking this term, the term which is inside the braces as u. So taking u as x plus natural logarithm of x, you get y is equal to u square. So dy by du turns out to be 2u and du by dx turns out to be 1 into 1 by x. Thereby solving, you get the answer 2 into x plus natural logarithm of x into 1 by x. I hope you understand how to apply the chain rule. Let us solve some more problems so that we can understand that how the differentiation was performed even without the chain rule. Likewise, over here, you can apply the chain rule into solving this problem also, wherein y is equal to x square plus 2 whole to the power 2 by 3. You can solve this problem by assuming x square plus 2 as u. What we had done, that y is equal to x square plus 2 whole to the power 2 by 3. So you can assume u is equal to x square plus 2, and you can say y is equal to u to the power 2 by 3. And then applying the formula, power formula, that d dx of x to the power n is equal to nx to the power n minus 1. You apply this formula over here, then you will get the question that d dx of u to the power 2 by 3 turns out to be 2 by 3 into u to the power 2 by 3 minus 1. That turns out to be 2 by 3 into u to the power minus 1 by 3. And derivative of u is also required because you are taking continuously the function part u as x square plus 2. So that's why when we are solving such type of numericals wherein y is x square plus 2 to the power 2 by 3, then derivative of the u is also required to be performed. So that means you are supposed to determine du by dx also. So du by dx will be d dx of x square plus 2. So solving d dx of x square plus 2, you will get the answer 2x. You will get the answer 2x. And solving this part, you will get the answer 2 by 3 x square plus 2 to the power minus 1 by 3. Solving the entire expression, you will get the answer 4x by 3 into x square plus 1 to the power 1 by 3. For your better clarity, let me solve it separately for you. So the question given to us was y is equal to x square plus 2 to the power 2 by 3. You can solve this numerical by taking u is equal to x square plus 2. Taking u is equal to x square plus 2, you can write y is equal to x square plus 2 to the power 2 by 3 is equal to u to the power 2 by 3. So that means dy by dx by applying chain rule will be dy by du into du by dx. So what will be dy by du? Dy by du will be equal to ddu of u to the power 2 by 3. Applying the power rule, that is d dx of x to the power n is nx to the power n minus 1, you will get 2 by 3 into u to the power 2 by 3 minus 1. That is 2 by 3 into u to the power minus 1 by 3. So we got dy by du. Now what is du by dx? Du by dx will be d dx of x square plus 2. That is nothing but 2x. So applying the chain rule, dy by dx is equal to dy by du into du by dx. So this will be equal to 2 by 3 into u to the power minus 1 by 3 into du by dx is 2 into x. Substituting the value of u in this expression, you will get 2 by 3. What was u? U was x square plus 2. U was x square plus 2 to the power minus 1 by 3 into 2x. So that means answer is, by solving, is 4x upon 3 into x square plus 2 to the power 1 by 3. So this is the solution for the expression y is equal to x square plus 2 to the power 2 by 3. And this is what we got. This is the solution. Just follow the steps which are given into the in this session, and try to solve the 4 numerical problems are given over here. and you will find that by applying the chain rule, you can directly determine the differentiation of the functions given to you in a very easy manner. The next important concept is differentiation of the parametric form. Again, the differentiation of the parametric form is quite simple. You just need to remember that if we are given a parameter t, you can write, or you just remember dy by dx can be written as dy by dt into dx by dt. Differentiating numerator and denominator with respect to parameter t, and you will get the same value dy by dx. So that means we are not going into the details of this part, but it is very simple to understand that dy by dx given the function y is equal to ft by gt or gt by ft, you can say gt by ft also. Then by applying the fundamental theorem, that is limit x tends to 0, fx plus delta x minus fx upon delta x is nothing but dy by dx, you can come to the solution that dy by dx is equivalent to dy by dt into divided by dx by dt, where t is the parameter. We are just going to apply this expression, this formula to solve the problems. Say we are supposed to find dy by dx, wherein x is equal to natural logarithm of parameter t and y is 1 over t. Then we are supposed to find, because we learned that dy by dx is equal to dy by dt upon dx by dt. So what will be dy by dt? Dy by dt is d dt of 1 by t. You can say d dt of t to the power minus 1. Applying the power rule, nx to the power n minus 1, ddx of x to the power n is nx to the power n minus 1 minus 1 into t to the power minus 2, that is minus 1 upon t square will be dy by dt, dy by dt. And we are given x is equal to natural logarithm of t, so dx by dt is nothing but 1 over t. Now applying the differentiation for the parametric form, we can write dy by dx is equal to dy by dt divided by dx by dt. We got dy by dt as minus 1 upon t square, and we got dx by dt as 1 by t. Solving, we get minus 1 by t. So this is the differentiation. Given the two variables x and y in terms of the parameter t, you can find the differentiation of y with respect to x. So let's extend our discussion to the second order derivative, that is the derivative of the derivative. So the second order derivative, that is d2y by dx, is nothing but ddx of dy by dx. So we are differentiating the derivative. So if y is equal to fx is a function and f is differentiable function, then derivative of dy by dx is also a function, and it itself should be differentiable. So we are not going into the details of the theoretical aspects. So far as the numerical aspects of this second order derivative is concerned, the d2y by dx square expression is ddx of dy by dx. Let's apply this understanding to solve the numerical. We are given y is equal to natural logarithm of x by x, and we are supposed to show that d2y by dx square is equal to 2 times of natural logarithm of x minus 3 upon x cube. Because d2y by dx square is ddx of dy by dx. So firstly we need to find dy by dx. So dy by dx will be equal to ddx of natural logarithm of x by x, and we can directly either apply the quotient rule or we can apply the product rule by rewriting this expression as x to the power minus 1 into natural logarithm of x. So ddx of x to the power minus 1 into natural logarithm of x. Then applying the product rule. What was the product rule? The product rule was ddx of fx into gx is equal to fx into g dash x plus gx into f dash x, where g dash x and f dash x are the first order derivatives of the respective functions f and g. So, applying the product rule and applying the respective formula. So, ddx of x inverse into ln natural logarithm of x into x inverse plus x inverse into ddx of natural logarithm of x. So, what we are finding? We are finding applying the product rule. Now, applying the power rule, ddx of x to the power n is equal to nx to the power n minus 1. So, ddx of x to the power minus 1 turns out to be minus 1 x to the power minus 1, that is minus 1 x to the power minus 2. So, this is the first derivative part. Second is ddx of natural logarithm of x, and we learned that ddx of natural logarithm of x is 1 by x. So, this turns out to be x inverse into 1 by x. X inverse into 1 by x is 1 by x square. So, this expression is now required to be solved. So, this turns out to be minus 1 upon x square, or you can say minus of natural logarithm of x by x square plus 1 upon x square. So, that means x square and 1 minus natural logarithm of x, and which can be rewritten as x to the power minus 2 into 1 minus natural logarithm of x. So, this is dy by dx. Now, we are supposed to find d2y by dx square. So, differentiation of this expression is now required. So, now we are going to differentiate this expression, because d2y by dx square is actually ddx of dy by dx. And what is our dy by dx? dy by dx is nothing but x to the power minus 2 into 1 minus natural logarithm of x. So, again applying the product rule to find d2y by dx, we are supposed to apply the product rule. That means ddx of x to the power minus 2 into 1 minus natural logarithm of x plus x to the power minus 2 into ddx of 1 minus natural logarithm of x. Differentiating by applying the power rule, that is ddx of x to the power n is equal to nx to the power n minus 1, and applying the differentiation of natural logarithm of x, that is ddx of ln x is equal to 1 by x, and applying these formulas into this expression, you will get finally the solution as minus x to the power minus 3, 2 minus 2 into natural logarithm of x plus 1. So, this solution actually turns out to be 2 into natural, because 2 plus 1 is 3. So, this is 3 over here. So, rearranging, because minus sign is outside over here, the final solution turns out to be 2 into natural logarithm of x minus 3 upon x cube. This will be our d2y by dx square. So, that means double derivative is derivative of the derivative. So, in order to find the derivative of order 2, that is second order derivative, we would firstly need to find dy by dx, and then whatever expression is found as the final outcome of dy by dx, we again need to differentiate it with respect to x. As in this case also, we firstly found dy by dx, and dy by dx was found to be x to the power minus 2 into 1 minus natural logarithm of x. Then again we differentiated this expression by applying the product rule, and we find that the final solution is this. It is advised that if it is possible, transform the try to apply the quotient rule to the minimum, because it has got a larger number of calculations, as we had done over here. Ln x upon x, that is natural logarithm of x by x. This we can directly apply the quotient rule, but in order to simplify, we transform this expression into the product form and apply the product rule. So you will understand these tricks when you are going to solve more and more numericals which are given in your self-learning material. I again recommend you to go through your self-learning material, go through these sessions, understand the concept which are delivered in these sessions, and then apply these concepts to solve the numericals given in your self-learning material, so as to have the better understanding. If you are having the better understanding, then only you can extend your understanding to apply for next unit is actually application of derivatives. So if you are not able to calculate the first order derivatives or the second order derivatives, then you will not be able to understand the unit number 2 of this block, calculus, that is application of derivatives. In our subsequent sessions, we are going to explore more and more problems wherein you are going to apply the understanding of differentiation to solve the practical problems, and that will be covering our next unit, application of derivatives. Thank you.